Alright, time for another DraftScience video presentation. Okay, so we had a couple of comments, yeah, sort of. The Batter Dirk guy said I goofed up, which I don't know exactly what that means, but anyway, you might like the channel Alien Scientist. Well, don't like the title much, and just glancing at it, anything that's defending any of this alien visitation bullshit is just that bullshit. It's not good science. It's going to be crap. So, yeah, sorry. They're doing some physics things. Yeah, who knows what kind of junk. So, interviewing engineers, etc., trying to cut through the BS, or why they make some BS, I would imagine. So, anyway, don't really see the point. I mean, conventional physics is garbage, but alien physics, yeah, it's even more garbage. So anyway, this was an interesting one. Aero Soap Breeze. Left a link. This is the best video I could find on the double slit experiment. Can you please go over it with your commentary? Well, I will explain, I guess, I mean, my commentary is, oh shit, the fact that he goes to all this trouble to do an experiment and is doing it, just looking at it all wrong, and trying to put use the glasses of conventional nonsense on top of it, and so it has all these wrong assumptions built into it, and so that's kind of depressing. But what are you going to do? Kind of a depressing name, Huygens optics, 400-year-old optics. I mean, not that some things don't change, but I just mean, Huygens was wrong. I mean, this whole wave thing was just such a huge mistake. So this part, I guess we could have lived without.
Hello everybody.
There we go.
This video is about the double slit experiment. And maybe you wonder why somebody wants to make yet another video about...
Right, well, they should make a video about it. They should then point out how Young's drawings don't work. They mathematically fail. So, we name something after somebody. It's supposed to demonstrate something. Again, Young didn't even see the two patterns. It's far short of a good beginning.
A more than 200 years old experiment, especially with already tons of videos on YouTube regarding the subject.
Right, and they're all bullshit. Everything I've played, that one, played that one, played that one, played... Oh, this one, the Al-Kahari one, is the most full of shit.
Well, for one, most videos don't show you the experiment, but just show you people talking about it.
Yeah, they show you the pattern, but they don't go into much depth into what causes it, and either do you, in the sense of you're not showing us how the geometry matches, how the math works, how this is, you're doing the same thing. You're just showing us pattern and saying, well, presumably this is what's causing it, but you do nothing to demonstrate that that's what's causing it, but you do nothing to show that the geometry is right.
This video, we'll have a look at the real deal.
So, yeah, I don't think that's what you would call it, actually. So, what's glaring, these are two slits. So this is, the patterns of two slits. And you can see the glaring thing is there's no light in the center. It's kind of strange, right? I mean, that the center of the slit would be no light. So they're very, very small slits, and so the argument would be I would make the argument. So I mean, he really isn't going to go, he's not going to give you any of these details, so I might as well go into it because he's not going to show you these details. I mean, in any realistic way, in any in-depth way, in any useful way. Oh dear, camera sliding. Well, not much I can do about the failures of the camera. Anyway, I guess I could turn the light on, but screw it. Oh. Alright, so what he's doing is he's doing this under a microscope. And so the really gigantic advantages, so I guess I could draw it this way. When we view the pattern, we're seeing a tiny percentage of it because of the distance the light has to travel and how much it has to, how few photons have to make the little pattern, right? I mean, it takes a lot of photons to make light go that far and then us to be able to see it with our eye. So you need a lot of photons to get to the surface to see it. And the other disadvantages is so we're only seeing a slight arc, right? I mean, the pattern's going out here and out here, but we don't see any of that because there's not enough intensity of the pattern out here, so we don't get to see any of that. So with a microscope, you're zooming in, so this arc gets much smaller as you get closer, and so you can see more of the pattern with your microscope lens up close, so you're catching a lot more of it. The disadvantage is that the magnification that happened this way, you weren't using, here you have to use just these infinitesimal slits, and the problem with the infinitesimal slits is essentially the polarization of the light is much larger than the slit, and well, at least as large, and so you're less, you won't have like a photon to get through the slit. So what's you're seeing there, the darkness of the centers of his pattern, okay, like no light's going straight through. Well, that's because all the photons are getting disturbed by the surfaces. None of the photons are going through the center undisturbed. They're all getting broken because, say, they're this size or this size of their polarization. They're breaking as they go through, and so you're not getting any whole photons going straight through, and all you're getting are the fragments, okay, that do combine in locations from the two surfaces. And but the problem, so you'll see a lot of single slit pattern in this double slit because, as I pointed out, the double slit relies on there being if there's too little distance between the slits, it's essentially mathematically the same. You can't make two path lengths differences that are a wavelength of difference if your slit is too narrow, even at distances. It's not a wavelength of difference. The wavelength is this size, and your distance you're viewing it at is way too short. So he's doing it with a microscope, so he's getting very short distances, and it's really hard to have a wavelength of difference. So you're losing this, these aren't two surfaces anymore. They essentially are seen as one surface and one surface. And so now you've kind of converted the double slit back into the single slit, because you're really just saying there's point source here and there's a point source here, and then you're doing this construction. Where if you really want to do the double slit correctly, you want to have no tiny distances between surfaces. So you want the slits to be big enough and you want the distance between them to be big enough so you can actually combine the four sources to one location and get a bright spot. Then you're going to get the real pattern because you're going to have all four sources will make their contribution, and then you'll see the real, double slit pattern. So he's not going to be able to see these bars at all because of how tight he's gotten it. These bars are going to be so small that he won't be able to see them, even with a microscope. And all he's going to really see is these will be the bars you'll see in the image. You'll see this, and you'll see this, and you'll see this. So you're going to see the envelope pattern, but you're not going to see the stuff inside the envelope. All right, that's probably enough of a preface. And down, and then I move this over, and then I play the video.
And because I show you my own version of the experiment, there is a good chance that you will see aspects of it.
So it doesn't look anything like familiar. It's like, what the hell is all this? So he's got, these are the two slits, and then he has them. As he goes in, you're basically converting it from the two slits, seeing what the two slits are producing, to seeing a mixture of the two slits. So as you go further out, you're able to see more of the other vectors. When he's really close, you can't see any of those, the one going from over here to over here. You're not seeing the combinations when you zoom in too much because there's not enough room. Now, the other problem with how he did the experiment, well, I'll wait till that image shows up and then I'll explain.
That you have never seen before. So, in the first half of this video, I'll discuss the experiment and the results. And in the second half, I will discuss the quantum mechanics behind it.
Now, he says he's not an expert on that kind of stuff, so he's just regurgitating the conventional theory, and it's based on the conventional assumptions and blah, blah, blah. So it's not very valuable.
My version of the experiment uses slits that have a width in the order of only a few wavelengths of light.
So that I'm not too sure of. I have to figure out how many nanometers this is. So wavelengths used is in nanometers, and so 5.54 and 0.6 UM. So 0.54 would be the 535. So he says a few, but obviously 25 would be 50. Okay, 50 wavelengths. See, the number of wavelengths really is telling you how many possible matches you have. So at these very tiny ones, okay, so that's still that's 5. So you'd get 5 points where you could have interference, quote unquote, where you could have possible wavelength differences. I mean, the irony is you have to have wavelength differences in the length of the geometric lines. Obviously, you can't have a wavelength difference, if your slit surfaces are too close to each other. How could you have a wavelength of difference in the lines you would draw from those two surfaces? So I'm just saying this is where he didn't go into any of the math, and so or the geometry. So the explanation would be this creates 5 bars, 3.5 creates 7 bars, 7 creates 14 bars, 13 creates 26 bars, 25 creates 50 bars, that kind of thing.
Which is actually significantly narrower than used in most experiments. And we will study diffraction under...
And again, it has a huge disadvantage in the sense the narrower you make the slits, the less possible it is for there to be wavelengths of difference in the path lengths.
A microscope instead of at a large distance on a screen. Now, this allows us to look at a few aspects of the experiment with much greater...
So again, you can see that where the slits are, there's very little light, and that's completely anti what your expectations are, that the middle of the slit, the single slit pattern done with traditional widths, the center is very bright, right? Extra bright, extremely bright, like 90% of the light goes straight through the slit. And clearly you have to go really, really tiny to start getting this artifact or defect or this piece of information. And the piece of information is kind of glaringly telling you no photons are getting through the slits. They're all getting broken by the surfaces. That's what it's glaringly telling you. I mean, all the math that works acknowledges that the surfaces are the place where the action happens. All of the fringe pattern comes from light that hits the surfaces. It goes right next to the surfaces. The surfaces are the point sources. That's the math that works. Young's math of the point sources being right in the middle of the openings, that math doesn't work. The geometry is wrong. You'll get the wrong location for the light and dark spots. So it's clearly all created by the surfaces, and that's obviously something this guy hasn't figured out yet. That it's not about slits, it's about surfaces. So the single slit is the two surface, the single impediment is the two surface, and then the double slit is the 4 surface experiment. But clearly, like I said, these dips right here, right where the slits are, that's telling you the slits are so narrow that photons aren't doing very well trying to get through them. the fat photons are hitting the surfaces a lot. Almost every photon is interacting in some way or another with the surface. Some piece of the photon is hitting the surface.
Detail. So to perform the experiment, I made various slits ranging from 2.5 to about 25 microns. And in the experiments, I also varied the distance between the slits.
So he doesn't show us any of that or tell us any of that or show us what image is which one. And so again, the distance is important in terms of the greater the distance, the wider the separation between the slits, the narrower the bars. So you can understand when he has them far apart, the bars are so narrow, he won't be able to see them. That's the disadvantage of using a microscope.
So let me first show you what you actually see in the experiment, and after that, let's have a look at how the experiment works and how the images were made.
So not nearly enough detail, this, frankly.
Here we're looking at the cross-section of a laser beam showing the intensity distribution.
So I don't know what that image was, but certainly wasn't very helpful.
And this beam is sent through.
Okay, so this is where you're starting to see the two slits. So he has a diagram here, there's two slits, and clearly nothing in the middle.
Two very narrow slits of approximately.
And then he's zooming in, I suppose, with the microscope to see where the two beams are crossing each other, okay, theoretically. The diffracted photons, the bent photons, are now being visible because he has to go in to see where the bent photons are.
3.5 microns wide. And this is what you observe after.
Alright, 3.5 microns wide. So this was like 7 bars or something per slit or something like that.
The light has passed the slits. It spreads out in these bright and dark bands.
So this image is not very helpful, frankly. I mean, he's not showing us a static image at a static location.
Especially in the direction perpendicular to the slit. By the way, notice how the individual slits are not spreading the light as a uniform.
Well, so this is part of the image problem. Is, like I said, he's not seeing the little bars that are actually in these bigger bars, theoretically. No, that's probably the wrong way to say it. He's not seeing the little bars that are inside of these bars. But regardless, like I said, the geometry is not consistent with normal patterns, so the fact that he doesn't even go into the nailing down the geometry, like at what distances this is, and how far from the surface is this, and where in location is this
bump. And this is because of the scale at which we're observing. Basically, everything you see here happens within 1 cubic millimeter.
Right, the whole experiment, the distance the microscope is from the surface is inside of a millimeter. The slits are less than a millimeter apart. So it's really tiny, really, really, really tiny. And that has its advantages and it has its disadvantages, obviously. All right, let's see if he shows something a little better.
You can see
here.
that the pattern of the individual slits already contain a lot of interference.
Okay, so this is what, he's put on a scale of some kind, measured it or did something to draw these patterns. But again, you see the dip. So the center of the slit is producing less light. So just understand, that's what you're seeing here. The center is producing less light.
Structure before the light starts to visually interfere with that of the other slit.
So this is apparently by location. So this is because he's moving the microscope closer to the surface or further away. So he's moving the microscope further away. Yeah, so this probably needs to be drawn. Yeah, I mean, like I said, he just didn't provide enough information for, you really have to analyze what he's doing to figure out what he's doing, because he doesn't explain it. That's going to be a little too wet, but we'll have to endure. I could just pause it for a second. I suppose I could do that. Why not? Alright, should be back. Alright, so let's see. You have the surface with the two slits in it, and then you have the lens of the microscope. And so what he's doing is he's starting off with the lens really close to the surface. And so you can't see the two slits interfering because the arc of their spread hasn't mixed yet. So when the microscope is at that level, you know, should have drawn that bigger, right? Yeah, could have drawn that a lot bigger, actually. You get the idea, though. So the slits are here and the slit is here. Okay, little tiny slits. So when the microscope is close, right, it's only seeing this. You know, it can't really see the two of them mixing because he's too close. But if he moves farther away, then he can get the ones that are, you know, interfering with each other, so to speak. The ones that have the path length differences, so the arcs can now cross each other, and you can see where the two are mixing. So as he moves the microscope away, he's seeing more of the two mixes, and he moves closer, he's cutting off all the mixing because the little arcs are just going like here and here. Yeah, that's just a detail, but it's all important and such. There, you know, devil's in the details, blah blah blah. I mean, it's really important for science to get the details right and to be sure their process of elimination is, you know, coherent. So you can see it here. So he has a little chart on the side. So the yellow line's getting further away. So he's moving the microscope lens away from the image.
As we move further away, the light of the two slits gradually starts to interact. Here.
So it's interacting regardless. Anyway. So you're getting a pattern, but the argument I would make is because the slits are so small, you're really only getting the envelope pattern. You're not getting the real little liney pattern.
Here at the bottom you see an intensity profile plotted, and this graph shows you the sum.
So, you know, it's not consistent with the what you'd call the normal double slit pattern, in the sense that this doesn't have a very consistent geometry. And they certainly aren't going to show us how the math predicts this.
Densities of the pixel columns in a part of the image above the graph. Now notice how the interference pattern develops between the slits.
So the changes just have to do with the wavelength difference, right? So that's all something everybody should know, is that the location, all right, of the minima and maxima in space is changing constantly. So it's in yeah, it'll have to do. So at any, you know, it's not like the pattern isn't like, okay, there's a bright spot here in space and you're looking at it from here, you know, some location, and then the bright spot moves to this location, and then it's in this location, and it's in this location. It's, you know, that doesn't really work. It's pretty much, you know, because the two slits are, it's the light that goes straight is different than the light that's being bent from the surfaces. So that's what's got to be understood. And so the pattern is different at each level. So the deeper you go, the more different the pattern gets. Now another problem you can see in these images that'll show up pretty soon is that you have the same problem of viewing on a flat surface. You really screw it up, okay? Because it fattens everything. So as you go further out, you're magnifying. It's a distorted lens. On a flat surface, you're getting a distorted view. You have to view it on a curved surface, or the spots over here get much bigger. So where a node would only be this size towards the middle, a node gets fatter and fatter and fatter as you go out here. And if you viewed it on a curved surface, every on-off would be exactly the same size. So that's another viewing problem that the microscope also has. So the fact that he's viewing it on a flat surface means that you get a lot of distortion in what looks like the size of the bars. So not only is there location change in space, as you're viewing where the bars are, where the path length differences equal one wavelength keeps moving. Okay, so as you get closer, it moves to different places, and so you have to be aware of the fact. I mean, it's probably in this alignment actually. I'll have to think about that. Because you're not getting a full wavelength of difference here. What's a full wavelength of difference here won't be a full wavelength of difference here and here. So a full wavelength of difference is always going to change into a bias in, I guess, this direction. Okay, so this one, the higher one will be here, and then the next one will be here. So where the bars are in the space is going to change depending on how far in and out you are. So that's why those lines keep moving. As busy as looking at different locations, and at different locations, the bars are in different places. All right, continuing.
First here in the center, and later it spreads out over almost the complete extent of the pattern. You can actually measure that the interference...
Alright, so this is good for the purpose of you can see the huge, like how they're getting bigger and bigger and bigger going this way. So this is only one slit. This slit is blocked. And then this one, this slit is blocked. And this one is open. No, pattern slit B only. So B is open. So the dark spot is actually... Well, that doesn't make any sense. Yeah, I don't know what that wouldn't make any sense. This one has to be pattern slit A only. Pattern slit A only. This is supposed to be A. So that, it doesn't make sense just because they're getting smaller going out and they have to get bigger. So that doesn't make any sense. Yeah, so sorry. I can't make any sense out of that. And he's got two patterns here, and there's supposed to be only one slit. I mean, two patterns in the sense you have brightness, then dark, and then bright, and then dark, So the geometry is really quite distortive here. Hard to see how this could make any sense as a single slit pattern. But easy to see how if you combine these two, you could get this byproduct. When you combine this extra dark with this extra bright, you get this muddled mess here. And likewise here, this hard dark with this bright, you can see. So you can sort of see why you would get some of this pattern. You can see the overlap of some of these bars and how that could also create a pattern here. This dark goes straight up through this light, becomes a dark here. Well, some of it doesn't seem terribly coherent. Obviously, these are different images taken at who knows what, you can't get the microscope to perfectly the same depth each time. So, but nothing traditional in any of this. I mean, he's not going to be able to show us the math that makes this rational.
Pattern is quite different from the patterns you would get if you would just add up the intensities of the individual slits. What I show you here is...
So it isn't quite different. So he just said it's quite different, but no, it seems pretty logical actually. The two seem quite consistent actually. I mean, it seems quite consistent. This is very dark here, and this is not as dark, so this light has blended with this dark to create this pattern. It's not terribly inconsistent at all.
Individual slits. What I show you here is all experimental and not just some simulation. And I wanted to show you this first to demonstrate that the double slit experiment actually contains
Well, it is simulated in the sense you have edited the video, because obviously some of this was moving this way, which it shouldn't be doing. So, you've taken, a long bit of film and turned it into a short bit of film.
Way more fascinating details than are normally presented. In fact, even the single slit experiment is already pretty groovy by itself.
Groovy. And clearly under these circumstances, it's completely non-intuitive, right? So, I mean, one of the key things they'll argue about the pattern is the two surfaces, it's equidistant to the center, right? And that's completely gone here. There's no fringe in the center. Nothing. It's dead. And there's no light going through the slit, apparently. All you have is the fringe pattern. So again, this is sort of an indication that photons aren't really getting through here without being affected by the surfaces. And so this will tell you what tiny slits will do.
And you don't need fancy equipment to see these
It's pretty fancy, frankly.
things for yourself. You just need a $2 laser diode, a small lens, double slit, and simple microscope and a web.
Right, and you got to be able to cut the slits into the surface, and you got to have all of this, got to put all this platform together and not burn your eye out with the laser and figure out a lot of stuff.
Webcam. Now, the way I visualize the intensity evolution is by making use of the very shallow depth of focus that some microscope objectives have. So everything outside a very thin slice of space is out of focus and will reach the CCD sensor as a diffuse and dim blur.
Right, so he's just pointing out the microscope has a very short field of view, a little sliver of space, tiny bit of space in the space. So if you've used a microscope before, you can sort of see, you can just move through the layers of a water drop, depth-wise.
And in this way, the images display mainly what's going on in the focal plane and ignore almost everything outside it. Now, as I just showed you, a single slit also displays interference. And that is because even a slit of 3.5 microns wide is still about 6 wavelengths wide.
So there's a lot more than 6 bars here, so I don't have any way to account for what he's viewing, because frankly it doesn't make much sense. So I'd have to think about that one for a while, because it really doesn't fit. So it has to be more than that, because there's way too many bars.
And contrary to interference between slits, it's not easy to assign this interference to a specific location within the slit. But I guess...
So again, it's not the slit, it's the surfaces. It has to keep being emphasized. The surfaces create all the fringe pattern. See, I mean, you can't have the wavelength differences. I'm just saying that the math can't work for this. If he's saying the slit is that narrow, you can't draw the two lines to any distance and get a wavelength of difference. So it couldn't be interference. If you're going to argue it's an interference pattern, it can't be interference if you can't make this line twice as long as this line, right? I mean, well, maybe this is important enough to draw it, I suppose. So I'm just saying where this breaks down with what is he's making a claim here. I mean, an assertion anyway. He's claiming that this is the distance he's using, and those distances can't possibly produce the pattern he's showing. And the argument is that if you have a certain distance, and then you're saying the wavelength of the light is a certain distance, the wavelength of the photon. Now, I would argue the photon is really a composite object of more than one bit, so you have to think about its whole length, but that's a whole nother subject. So we're talking just a wavelength of difference, that is the wavelength of the light, which is pretty big. 500 nanometers is really large. And so the problem with what he's doing here is if he's saying this slit is only, say, 5 or 7 wavelengths of distance, to get a full wavelength between this location and this location, you need a full wavelength of difference for there to be an on. And you can't get it with this short a distance. You have to go, you have to go way over here to get a full wavelength of difference. You see what I'm saying? I mean, you have to go way over here. You can't get one here and get one here and get one here and get one here and get one here. You can't get them at these locations because there can't possibly be a full phase or wavelength of difference. So something doesn't match there. That's all I'm saying. Something doesn't fit. Not just my theory, but conventional theory.
The interference is originating from the fact that the slits are so very narrow that they only allow specific wave modes to exist within the confinement.
So wave modes, I mean, this is just kind of, baby talk, whatever, wave modes. There's no wave modes, whatever the hell that is. There's wavelength, path length differences. The pattern is made out of path length differences. That's the geometry of wave interference, is path length differences, not wave modes.
Of the slit. Here you can see what happens if the light passes a wedge-shaped slit.
Alright, so this is narrower at the top, right? Narrower at the top, wide at the bottom. So the narrow slit should give you the wider bars, and the open slit should give you the narrower bars. The greater the distance, the smaller the bars. The smaller the distance, the bigger the bars. So you got big bars at the top, small bars at the bottom.
Ranging in width from about 2.5 microns here to about 25 microns here. At the higher widths, you can observe this low frequency component superimposed on the interference pattern.
Low frequency component superimposed, blah blah blah. Who knows what that is? Sorry. Doesn't mean much to me.
And I guess these are sort of...
The problem also is here is you get, some of the light is not just bending out, it's bending these kind of directions depending on how perfect your slit surface is. So if you have any, when you're making these really tiny slits, you got a lot of jaggedness in them. And that jaggedness means that there's lots of other angles that the light bends at. And so they ends up bleeding into... So doing a slit that has a shape to it, that has any kind of jaggedness in it, means that the two surfaces are going to bleed into each other. And that's sort of what's happening here, is you're not really... It's you can see that the bars at the bottom are much smaller as they go out, but there's a lot of interference close in, and that's being caused because of the defects and the imperfections in the surface.
Interference phenomena between the different wave modes that can exist within the slit.
So again, more different wave modes is just, what is a wave mode? I mean, what is that? I'm supposed to know what a wave mode is. Sorry.
Diffraction can either be described in the classical way by the Huygens principle of wave diffraction, or with quantum mechanics by the Heisenberg uncertainty.
And both of them are hugely flawed. So again, the wave mechanics doesn't really work unless you consider the sources to be the surfaces. So I'll go over this, I'll reiterate a fundamental point. I mean, it's just vitally important to understanding any of this crap, is understanding that it's all about the surfaces. And that's all that's in the math. The math that works recognizes that the surfaces are doing all of the radiating. Okay, and it's all you're doing is you're just saying we're radiating, and then the radiation is mixing. Okay, so you got these points where you're combining a source from here, a piece from here, and a piece from here. So those are going to be your two waves if you want to make them two waves. But obviously, if you put the two waves in this weird location, here's your solid surface. That's a pretty weird way. It's a pretty weird location for the wave to be, is on the surface, right? So, I mean, the Young drawing had the wave coming out, just like this. That math doesn't work. This is the point source, doesn't work. These have to be the point sources. So these places have to be where the waves are. And again, all of the pattern can be geometrically understood to have to come from components from the surfaces. The surfaces create all of the fringe pattern. And anything going here is just light that went straight through. And again, he made these slits so small that the light polarization being this size, let's say, you can sort of see that no matter where you locate the, it's likely that a piece of it's going to get broken off. I mean, the only light that could get through would have to go exactly right through the center, And so that's kind of improbable. Most of the light's going to be a little bit over, or a little, touching a little bit. And some of it's going to be touching a lot. And so the surfaces are where you're creating the fodder for the pattern. And I would argue the sensible thing to understand is what you're really doing is breaking photons and then merely putting them back together. Photons are just a sequence of radiation at a specific period. And all you're doing is breaking that, taking a piece out. On this surface, you took a piece out, and only a piece went here, and a piece went here. And then you're just combining it with pieces from the other surface to remake the pattern. When you're in phase, you have a photon. When they're out of phase, no photon. You have a 50-50 chance of putting the photons back together. You're throwing pieces at the wall, and you're just saying it's 50-50, whether they're in phase, whether I've matched the pattern, or whether I've got a piece in the wrong place. And it's a 50-50 chance. So this drawing is really, even though he's doing this stupid Heisenberg crap, look at the triangles, right? I mean, the triangles are coming from the surfaces. Those are the places where you're getting the mixtures from. So the sources are the surfaces. That's the important fact. It has nothing to do with Heisenberg. It just has to do with, that's what's causing the pattern, is the surfaces. Just has to be reiterated. And when you have two sources and you have two sources, you square the number of possible matches. If you have two sources, this can only match with this. But if I add this, then this can match with this, and it can match with this, and it can match with this. You get it? So you have more potential to make matches when you have two slits.
Principle. Now, since later in this video I'll discuss the quantum character of light, I will focus on the explanation of diffraction as depicted by Heisenberg.
So again, this isn't a depiction of diffraction in the sense that any other sense than this is what you could understand particles to do. Anything that leaves a surface at an angle. So you don't need to believe in any uncertainty principle to understand that photons can be disrupted by traveling next to a surface. Obviously, surfaces are full of disruptive. That's why light diffracts on the surface of water. Surfaces are interesting places. And if the light's going right by the surface, there's every probability the light's going to be bent. Just as there's every probability it's going to be bent going into a surface.
The Heisenberg uncertainty principle states that the position of an object and its momentum cannot be independent.
So again, this shouldn't be momentum. It should be its direction also. Okay, so it's not just its momentum. But clearly the photons all have the same momentum. Frequency doesn't change its momentum. It just means that you're throwing more rocks per second. Yeah, obviously if I throw more rocks per second, there's going to be more rocks in the air. Okay, but it doesn't mean that each rock has more energy. The momentum of every photon, every component of a photon, the composite little bits that are actually creating this pattern all have exactly the same momentum.
Determined with a very high precision at the same time. And that is the case for all objects, either large or small.
That's not the case. This is just religion, frankly. His chosen religion.
In essence, the product of the uncertainties in these properties should always be bigger than the value of this particular constant, which, by the way, has a very small value. Now, the thing is that when you're trying to get information about the position of an object with increasing precision, The uncertainty.
So this is the the silly part where they say the only part of the universe we can't nail down, we can't see, is the part we can't see. So the unseeable part, the part that has all these wacky features, just happens to be the part we actually can't see. So it's not the fact that we can't see it. That's not why it's wacky. It's wacky innately. And that's sort of their evidence. I mean, there's nothing more to it. They're just taking advantage of the fact that we can't prove them wrong. Because we can't take a photograph of a photon in space. So they're just making this crap up, essentially. There's really no good reason to believe photons don't travel through discrete, hard, real space, just like electrons, that they have any such thing as a wave function, or that they're in any way confused about their identity. No good reason to believe.
The uncertainty about its momentum must get bigger. And this phenomenon can best be observed in small objects like elementary particles and light quanta. Now, in the case of light going through a very narrow slit, and especially near the boundaries of the slit, the increased certainty about the position means that the uncertainty in momentum will go up.
So the boundaries of the slit, he said, implying that the surfaces matter. Well, that would be completely against what Feynman says, and that in a sense is against what Heisenberg says, because they're basically arguing that every photon is going through this uncertainty process with equal amounts of uncertainty, even though you can logically understand, no, the ones that go through the center of the slit don't bother with any of this uncertainty principle crap. They're not at all turning into wave functions.
And for light it means generally that it will spread out. The way I made these slits is by etching the patterns into a thin chromium layer, and I used old lithographic photomasks for this purpose.
Yeah, we all have that. So again, it's not exactly an easy to duplicate experiment in the sense that, yes, I know I don't have etching material, and I can't etch slits, and I can't photograph them and do that. I mean, yeah, I don't got all that crap.
To etch the patterns I used a photoresist layer and exposed this layer with UV light in the pattern of the slits. After that, the photoresist was developed and the chromium underneath was etched in the desired pattern.
So again, it's really small, and the problem is it's just almost impossible to etch these perfectly straight lines on very, 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 very small lines. Very hard to do.
And the result is tiny transparent slits in the chromium layer. By the way, the exposure patterns in photoresist were produced by using the
He's got a microscope. He could have taken, probably could have shown us what the slits actually look like under the microscope. So he could have shown us their imperfection or perfection.
Self-maskless wafer stepper that featured in several of my previous videos. And here's the measurement setup. For the experiments I actually used two different lasers, a green laser diode and a red helium neon laser. They both worked fine, however, generally the beam quality of the helium neon laser was a bit better. So when using the green laser, light was collimated.
So again, this really does require, because you're doing it under a microscope, all of the little defects are going to show up as you're using such a tiny percentage of the light. Obviously you go blind if you were shooting the actual laser into the microscope. So yeah, he has to use something to, prevent that. And so the advantage of doing it with a lot of light is you take away all of those defects and project the image big. And the problem with the smaller you go, the more each one of those little defects in the surface will become more and more important.
With a small lens and then...
And the defects in how perfect the light source is become more important. I guess that was the more important point. The less culminated, the less in alignment the photons in the laser are, all of that becomes more important when you're doing it in a microscope.
Projected on the slits, which were etched in this disc placed on the table of the microscope. In the case of the helium neon laser, I just used a beam splitter to direct the beam upwards towards the slit.
That for what purpose? Okay, used a beam splitter to direct the light, so he shot it through a beam splitter and then up. So, yeah, I don't know how perfectly culminated that is then. I mean, the beam splitter is basically saying, let's, create a pattern in the light itself, which probably isn't a great idea.
On the other side of the slits is the microscope that can be moved from and to the slit pattern, and the objective of the microscope projects the light on the CMOS chip of a camera, which sends the images to a PC. It may not look that way.
So he has all these, details about how he did the experiment, but not much about the actual experiment, which is,
But in a monochromatic beam of light, such as the one generated by these lasers, the energy contained in the beam can only have very specific values. In other words, the energy is quantized.
All right, so this is where they really go south, okay, is in understanding what a photon is. First, they don't understand it as a composite object. They don't understand it as something that happens over a period of time. They think the photon's frequency is a clump, and that's it. So when they say wave, they mean just one wave. That's it, one wave. Boom, that's a photon. When you could logically understand that the reason why the surface knows it's a frequency is that there's more than one wave, and that's how it knows one frequency from another frequency, is that the reaction is going to be to a sequence that's going to take place. A sequence hits the surface. And you can sort of know this from the fact that polarization of the light, that is the size of it in space, is huge. 1,000, perhaps 1,000 atoms across. So even though it's made of tiniest little things you could imagine, those tiny things must have more than one component because they have to have a separation. So obviously a single electron, the photon has a polarization that's 1,000 times, 1,000 atoms. How could the photon interact with one electron? So when we see, when he draws this pattern, why is he drawing this pattern? He's not drawing this pattern because he saw a photon. He's drawing this pattern because a piece of electricity was created, both for the camera and for your eye and for even a photo detector, a photo multiplier. They're all creating electrons. That's how it knows a photon hit, is counting electrons moving. You don't see photons, you see electrons move. You see electricity. So that's why it's clumpy, is because you're only going to get a photon when you create an electric current. That's the fact of it. You have to create an electric current to create a photon, and to see a photon. To say there was a photon, electricity has to be created. We can't see a photon any other way than to watch it create electricity. So that's number one, we only have clump detectors. And then, number two, I would argue that the bits of the photon, are the energy of the photon. And that energy, if it's not in the right pattern, we don't see it at all. Just like right now, you're not seeing cell phone energy hitting you. You're not seeing microwaves going through you. You're not seeing radio waves going through you. You're not seeing any of that stuff. Still there, but you're not seeing it because no part of you is creating electricity because of it. You're not buzzing with the electricity it's creating. Where your eyeball is made to create electricity when photons hit, the receptors. So they're made to detect. But the rest of us isn't, nothing else is made to detect, so we don't see. Doesn't mean the energy didn't hit us. Didn't mean it didn't interact with us. Didn't mean it didn't heat us up. So, you have to be, to say a photon is that little block is just sort of deceptive because the photon isn't a little block. The photon it causes an effect. Photons have to make an effect. The effect is an electron block. But if you don't have all the right pieces to the cause, you're not going to get the effect. So the photon is, in my opinion, kind of obviously a sequence of events. Could be 2 events, could be 3, could be 7, could be 500. But it's events that have to happen for there to be electricity and for us to say photon.
To increase the intensity of the beam, this can only be done in discrete steps. A bit like going...
You can only cause electricity in discrete steps as a little voltage, a little volt at a time kind of argument. An electron at a time. So this is just really saying we see electrons. Because we don't see photons. We see the electrons they cause. We see electrons move. We don't see photons move.
up or down a ladder. These steps are actually extremely small, and in practice you will only notice that light is quantized if you go to extremely low intensity levels.
Again, you can't go any lower than an electron. You can't have half an electron. You can't have an electron moved, this much. The electron has to be an electric current. That's when we can measure it. It has to actually be an electron that leaves an atom and does a specific thing. Moves to another atom, causing another atom to lose its electron. It has to cause a cascading electron sequence for us to see the photon. And you can't do half of that sequence. You can't have half a cascade, say, photon. So it has to cause the full event, or there's no event. So it's a tipping point argument. It either tips it or it just wobbles it. If it wobbles it, we have no idea. Still energy, did plenty of wobbling, but if it doesn't tip it, no event. So that's all the truth is here. The underlying truth is that simple, that we're having to see an event, a tipping, and there could be lots of wobbles.
In that case, you can get to a point where only a few or even just one of these quanta is present in the beam.
All right, so the argument again would be, no, that's not what you're getting. You're getting lots of energy, but we can't do this single photon thing. Okay, we can create it so there's very few electrons being forced to become electricity. We can do that, but we can't be sure what the hell we sent in terms of actual pieces of photon. So again, it just has to do with the fact they never even considered, no one's considering photons as composite objects. Everybody's arguing it's either a wave, a single lump of wave, up, down, there, photon. When they draw it, they draw this whole thing, right? But they don't account for their whole thing. They don't account for a bunch of events. They just say wave, the wave, that's it. Push, pull, done. That's a photon. And again, if they make it a particle, they say the particle has a frequency, which doesn't make any sense because radio waves would have to be a particle that would be miles long. Doesn't make any sense. No, there's miles between them.
So at that point, the beam contains only one individual package of energy called a photon.
All right, so this is another subject I've gotten into. It's so much more complicated, and they're just trivializing something there's more to it, and this idea that they can just make single photons. So the traditional assumption, and it's just an assumption, is that somehow the photon is like a cannonball or something. It's a little round thing, a little ball of something, and I'll put a barrier. And the barrier will mean that most of them can't get through. Some go that deep, and some go that deep and that deep. And they go all kinds of depth. But I've got it just thick enough where only a very rare one cannonball gets through, in a second. Okay, so millions of them crash into the surface, and only one actually gets through. But that's not really the rational theory. The rational theory was, again, to look at this like a beam splitter. That what's happening when you put a block in front of the photons is that you're essentially doing the same thing you're doing with a beam splitter. That is, you're creating a bunch of little openings. Okay, like the surface has weak spots in it. Okay, where, it's like little tiny slits. So there are little places where the matter creates a pretty good path. And some of the energy could get through those paths. But just like the narrow slit, the photon can't get through as a whole photon. So if this is the photon in space, little bits traveling parallel to each other. Can you see? Yeah, you can see that. In a direction. If this is the photon, you could understand that, a piece could come out of here, right? The other pieces got hit by they hit the surfaces. And one piece came out of here, and then one piece came out of here, and one piece can come out of here. And they could be in these different locations, and they're all going in scattered locations. And you could understand that at any one location, I could sit here and wait, and eventually, one will come out of here, and one will come out of here at the right phase, that is, the right distance from each other, and that'll reconstruct the photon. I'll get the right wavelength, I'll get the right pattern, and the right pattern will show up and cause electricity, right? And so then I'll say photon. Now, the photon I'm seeing wasn't made out of something that went through. No, it's made out of little bits. So in this field, so when they're saying they're blocking the light and only one photon's getting through, the truth is a lot of pieces of photon are in this field. There's lots of pieces, and it's only in the, these rare locations where you actually get the sequence right again. You have to have the right distance and the right number of photons, right? The closer you are, the more likely you are to have a photon. The further away, the less likely. All those kind of rules apply. But that's a more rational explanation than some kind of notion that I put 1,000,000 of them in and one miraculous cannonball flies through. Not likely. You're not likely to make a substance that's capable of just letting one through. Not a high probability. You either create a big hole in the dam or no holes, that kind of thing. It's really hard to make the little pinhole in the dam kind of thing, because it just automatically would get bigger, or it would automatically let too many through. It'd just be very rare that you could have an actual pinhole, where only one gets through.
And basically it has no way of interacting with others, since it's alone in the beam during its very brief existence. But the thing is...
So he's going to do it the same rationalization that Veritasium used when he did the single photon. He's making an excuse to do the experiment quickly. So instead of, creating so few photons that you only get like 10 an hour, right? You get 10 spots that say photon in 1 hour. So you're not getting many at all. And let's say you need to collect 1,000 or 10,000 before you can know what kind of pattern you got. Well, now you have to wait 5 days. You have to take 5 days to do the experiment now. And again, you still can't undo the fact that you don't know whether you're making these photons out of pieces of photons. So it doesn't really tell you that there's not 2 photons, that is 2 pieces in the experiment at the same time. And that's all you need, is 2 pieces in the experiment at the same time. You don't need 2 complete photons. You just need 2 pieces to hit the surfaces and go to the locations.
Even at these very low intensity levels, we still observe interference. So next I will show you the single...
So he says so, okay? So again, it's just this argument that we've got good evidence. And as I pointed out with the Veritasium video, it was clear the evidence was really poor, because he had to turn the photodetector all the way up to the highest sensitivity. So instead of doing the experiment with it on the most reliable, that is, you're sure the photon came from the experiment, he had it on the most unreliable. And this guy is essentially arguing to do the same thing. So instead of doing the experiment where you're sure there's only 1 photon, and the fact is it doesn't work. So when they're sure it doesn't work, and that's why he's decided to rationalize, is because it works if I do speed up the experiment. Then I can get the predicted results.
Photon experiment. In the current configuration, I did not need fancy equipment like photomultipliers and pulse counters. I just needed a few gray filters to bring down the intensity of the beam to below single photon level.
So I would argue there is no single photon that pops through this surface. Okay, that's not what's happening. The surface is breaking all of the photons. There's no path for a single photon. So just as the single slit, he just showed you that single slit, and it's a tiny slit, and you just saw where it was completely black in front of the slit. Directly in front of the slit was dark. No photons. So he's already shown you that a single slit that doesn't even have to be very small prevents photons from going through it. So you can understand that the little slits that are in this material, how tiny the little opening might be, has to be so infinitesimal that, of course, no single photon could actually make it through. The polarization of the photon, again, is 1,000 atoms. How can 1,000 atoms travel through that material evenly? There's no way you could get 1,000 atoms worth of size through a hole. So it doesn't make any sense. So obviously it has to be little composite bits. And so that material, even though he's saying one photon's coming out, no, a little bunch of little pieces are coming out in all kinds of directions. There's little scattered pieces of photon flying out. And you just have a really rare opportunity to be able to, where they're shooting out at the right angle and they have the right phase. So you have to match two things. They have to both hit the same location, and they have to hit the same location the right timing. And so, yes, it's a rare event, but you have lots of stuff hitting the surface. It's just that none of it's hitting it in the required frequency and at the required distance.
And to do this, it's not necessary to collect like one photon every second or so. You can collect many millions of...
So he's, like I said, it's not necessary to do the experiment over a long period of time. No, you can do it over a very short period of time with billions of photons. No, you really can't, is my argument. So he's basing all of this, he does all of this math, all this is to demonstrate, to make an excuse to compromise the experiment, and it's all based on assumptions. So the first assumption they make is that the photon, has that the size of the photon is the wavelength. All right, so if this was 500 nanometers, that's as big as the photon can be. Well, as I've just kind of pointed out, my argument would be, even if you believe in waves, you have to believe the photon is more than one wave, more than one hump. And if you're going to believe in particles, you really have to believe it's more than one to know the frequency, right? If it's particles, you definitely have to have more than one to be able to get the frequency, right? So those two theories right there pretty much tell you that, no, a photon is big, because it's going to have more than one event. It's going to have a wave here and a hump here and a hump here. That's going to be 3 of them will be a photon, or 5 of them, or 6 of them. So it's not until you have 6 waves does an electron do the right thing and create electricity. So it takes 6 waves to make an electric current, something like that. Well, now your size is much bigger. So now you're talking 2,500 nanometers, So now, you're talking about, here's your experiment that you're going through. You're going to detect at this point. This is where your slits are, your surfaces, right? The surfaces are more important than saying slits, of course. And so your argument is you don't want 2 photons here at the same time. You don't want 2 photons in the experiment at the same time, because then you'd have an excuse for the 2 interfering with each other. So they're trying to prove that 1 photon is all that's in here at this location at one time. But again, if I do the math based on this size, I'm going to get a very different answer than I do the math on this size, right? This is going to give me a different answer than this. If I'm saying only like this photon could be here, and the other photon could be here. Well, I still have the pattern here because I have 1, 2, and then 3. I can make it out of 2 pieces from this one and 1 piece from that one. So the odds of 2 photons being in the experiment changes if I make the photon into an event. Then the events can cross. This event can cross this event. Yeah, they didn't line up perfectly. They didn't come into the experiment exactly the same time, but they don't have to if all they're doing is putting pieces together here. So that's the flaw here. Is that all this math he does to prove that somehow 2 photons aren't in an experiment at the same time doesn't prove that. And again, the only reason why they would push this is because, like I said, why did Veritasium do the experiment the way he did it? Well, he did it because he tried it the other way first and it didn't work. That's why he did it, okay? That's the fact. The fact is, when he was sure there was only 1 photon in the experiment at a time, it didn't work. And so he had to push the margin. And this guy's making an excuse for the same thing. I needed to speed it up. I need to put more photons into the experiment. So I had to justify pushing it right to the mathematical limits. And that's all he's doing. He's giving you a rationalization for why he's pushing it.
Photons per second, as is shown in this calculation. I won't discuss it in detail, just pause the video if you want to take a closer look at the calculation. But the bottom line is that you can calculate the photon flux corresponding to, on average, 1 photon in the beam at any time.
And all that's based on your assumptions about what a photon is, what its polarization is, what its spatial dimensions are. And again, they don't account for any of those. Again, the spatial dimensions of a photon are huge. Thousands of atoms of polarization. 1,000 atoms anyway.
And for that you use the travel time of the photon between the slits and the CMOS sensor, which is 0.6 nanoseconds. Now, as you can see, the flux is pretty substantial, about 1.6 billion photons per second. But because of statistics, we have to get significantly below that value to be sure that the majority of all photons is actually alone in the beam. On the other hand, we can use the laser power and the photon energy to calculate the photon flux generated by the laser.
So again, part of what you can sort of intuit out of some of this stuff is that these filters don't get hot. So you're saying, well, if they're not getting hot, then the energy of the photons, the momentum of the photons must be getting through them. So this is another way to understand polarization film isn't blocking photons, because it really doesn't get hot, doesn't absorb the energy. And, so that'd be one way for them to find out whether they're really stopping the photon's energy by using an opaque filter, that's semi-transparent. Because a lot of broken photons might be getting through, but the whole photons aren't. So now you're back to reconstruction. And so I would argue that if you did measure things by heat, that the light and dark bands would disappear, because it's just as light in terms of heat where the dark bands are as it is at the light bands. Just as much energy is hitting there. It's just not in a form that creates photons, that creates the movement, the tipping of an electron. But you did plenty of wobbling. You just didn't tip. So if you measured wobble, you'd see that the pattern disappears, because there's the same amount of energy going to the dark places as there is the light places. And if you looked at that transparency, or that opaque piece of glass that you're using to filter the light, to knock down the number of photons, if you really looked at it as a heat signature, you'd see it's not getting hot enough.
Before and after the slits. And from this we can calculate what optical filter is required to get the intensity level of the laser beam significantly below the single photon level. Now, for the current helium-neon laser, we can calculate that we have to use a great...
So just to understand that he's got more explanations of these little details in here than details of the actual patterns produced by the experiment. So we have a lot more of this stuff than we have stuff showing us what the pattern was. And, that's sort of a giveaway, in my opinion, that he's not too comfortable with the fact that he had to push it.
A filter with an optical density of at least 2, meaning 1% transmission, to get below the 1 photon limit. So if we use an optical density filter of 3, we have on average only 0.09 photon in the beam according to the calculation. But just to be safe, I went all the way down to filters with an optical density of 6. So I dimmed the laser power by a factor of 1,000,000. And this brings down the average...
And these are all mathematical assumptions based on what your beam strength is and how narrow it is, and what filters you put it, what culminating lenses you put it through. So you change all of these numbers with one of those culminating lenses. You've already changed your numbers because you're making the beam smaller. So all those kind of things would change these numbers. So you really can't base these, you can't use these standard numbers and say your experiment is exactly doing that. You have to measure it by doing the experiment with no slits. So don't put slits in your experiment and see how many photons you're getting. And then put your experiment in and prove that you did the experiment in an environment where there were no photons, because you had to turn down so low. You have to do this in a controlled way, and there's no evidence he did that controlled experiment. He's not going to provide us any information to indicate he did that controlled experiment, where he first did the experiment with no slits, just see how many photons you're detecting. Did he do that?
Photon presence in the beam to 1 in 10,000. And it turns out that this type of single photon flux is easily seen by a standard camera in the current configuration. Now I should add a few remarks to that. The camera I use allows shutter times of 15 seconds, and it is possible to increase the sensor gain significantly. With the higher gain, however, I got a lot of thermal.
Yeah, well, I think it's more than just thermal. I think you're also getting something from your laser, which you've put through a beam splitter, and you're getting the pattern from the beam splitter. Especially when you turn the light down, that pattern becomes probably more visible.
Noise in my images. So what I did was cool the camera to about -5 degrees Celsius using a Peltier element.
Right, so this is another, wouldn't it be simpler to do the experiment over a longer period of time and then not have to cool your camera? I mean, see, these are the, kind of obvious questions. Well, why not just take an hour to do it, or 2 hours, or 2 days? Why are you forcing it to happen in this tiny amount of time, and therefore having to cool your camera and do all this other stuff because of the noise you're creating by having the camera turned up too sensitive?
And this suppressed any noise significantly. To demonstrate single photon interference, I took one detail of the interference pattern and collected the data at beam intensity levels ranging over. So
he took one piece of the data and then blew it up for some purpose and blah blah blah. But who knows? Is this the single photon data? That's a lot of data. Yeah. So one slit apparently is a lot darker than the other slit for some reason. And we don't even know if we have a full blend of the pattern here. So, you have two, there's some symmetry here anyway. You got 2 bars, and then you have a bar away from them, and then you have you have 2 dark lines, and then you have a double dark line. So, you have some symmetry, but it's certainly not the math. The math wouldn't predict that.
For 6 orders of magnitude. And here you see the results that were acquired using different gray filters and of course different shutter times and gain settings. And the result is actually amazingly clear. So whether photons are alone in the beam or whether there are many at the same time, the result of all these interference measurements is exactly the same.
So it's exactly, in some sense, opposite of what he got before, right? Is this the center line here? You have 0 photons in the center of the beam. It's not a very, I don't know what the green lines there are. So I don't know what these green lines in the bottom are. So, yeah, I don't know. So these are all with a filter. So he's not comparing them to the pattern you got without a filter. So, it's not making a comparison. He's just making a comparison with different filters. And all the filters, presumably, are, in my opinion, letting lots of pieces through. And that's why you're getting a pattern.
So this indeed proves that a photon does not need the presence of another photon.
So it doesn't prove it. So that's, sorry. Proof should be better than that. So, it's a claim. You can assert that it's a good piece of evidence. And I might argue that, I don't know if it's that good, actually. There are things here, right? You got, this lines are much higher than this side for some reason. Obviously this isn't the double slit pattern. You're obviously doing the focal thing where you've cranked the microscope close to the surface because it's really not the full pattern. You shouldn't be able to see the single slits. If you're far enough away from the pattern, you should be getting a full double slit pattern, not 2 single slit patterns. And you're basically seeing 2 single slit patterns there. So, there's a lot. This is a lot short of proof.
To display interference. So the conclusion must be photons somehow interfere with themselves.
Yeah, no, that doesn't have to be the conclusion. And it doesn't make any sense, and it's all kind of silly. So how do they interfere with themselves in the single slit? You showed the single slit pattern. How does a single photon go through the single slit and interfere with itself? I mean, isn't that one of the first questions you really have to be able to answer, and answer it in some sort of really decisive way? And what are you going to say? Well, Huygens says, there's an infinite number of little wavelets, and somehow the infinite number of wavelets know to break in half. That 50-50 somehow. Somehow I should create two waves in the opening. Two waves in the opening. When we know the math says it's right on the surface, so I have to create the two waves right on the surface. Why would a single photon create two waves on both surfaces? All right. So anyway, we'll call that a video, I think, and maybe we'll do the rest. The rest is all just quantum mechanic woo bullshit, but I suppose we might as well go through it. Quite tedious and irritating from my perspective. So anyway, so that's enough of a video and such. So this has been a DraftScience video presentation. Thank you for your attention and such.